So now you know my name. So this is, as it is, an experiment, so it's like not a proper research academic paper, but more like some experiences we had with low code. So about the term low code, now it's getting more and more popular. That we had been introduced also this morning. She talked a bit about this during the keynote. But the term was introduced 10 years ago, and that's mainly because there are more and more applications being developed. So people are really looking for ways to develop applications much faster than it is today. You know, there's a lot of complications, and that's why we talk about models. Models is a way to help develop the application. No code is an interesting topic to help reduce the development time estimated down to 50%. Sounds quite substantial. And of course, these these study groups like Gardner, they always very optimistic. So they say, well, by 2025, 70% of the applications will be developed using low code. Probably won't be the case, but anyway, it's an interesting aspect. Another thing is when you talk about low code, there's very often a confusion. You have low code, no code, and what we call IDT, Intelligent Developer Technologies, which includes AI, and also includes generation of frameworks to help development. So you can understand that between no code and AI, there's a huge gap. And what we really focus here in that experiment is more low code. We think it's more pragmatic. We think people need to write something. It cannot be no code at all. It doesn't really make sense. So you need minimal programming skills, maybe not programming skills, but at least some understanding of some concepts of what you're doing. Like if you talk about tech machines, might be advanced, but you have to know what it is. So, otherwise, you won't be able to write a state machine if you don't know what it is. If you talk about parallel execution, you have to understand what parallel execution means. Otherwise, it's going to be difficult to model something. But if your final application is using state machines or is using parallel execution, well, you should be aware of what it is. So you should be able to manipulate some representation of it and make the link with the reality. So it should make sense if you have a minimal knowledge of some programming concepts to be able to use low code. So if you look at the low code tools that are available, what they have basically is a set of pre-built components that people can just sort of drag and drop and build something. So it's a very constrained environment. So the tool sort of guides or prevents you to do things. It prevents you to do things. And then it makes a direct link, a direct integration with your final application, your final target, what you're aiming at. So, take for example, Microsoft Power Apps. It's basically a set of predefined layouts. Can you see something here? Yeah? So the laser, can you see?
The laser?
No, it's very small, huh? Okay, so anyway, on the left you have a bunch of predefined layouts. So it's like pre-organized layouts, and then you have components that you can drag, and then the components are connected to some real sensors or information, and to deploy on mobile phones or on web server, you can just drag and drop, and it makes all the connection and everything quite easily. So, well, you have a sense that, you know, there's no real programming here, but there's no real logic going on either. No? It's just like having one of these representations for I don't know, temperature, pressure, or something, a value, but there is no logic going on here. Okay? We are more interested in system where we have some logic going on, and we have to define what the logic should be in the system. So, what we believe that the existing tools, where you have this kind of low-code systems, they have their own notation. They never use standards. So they make up a new sort of notation, which is related, of course, to the operational concepts. But as I said, there's no logic usually. Of course, the major point here is that you have a better integration, right? Because it's a dedicated representation directly linked to the final system. But there's very difficult ways to extend to something else. As I said, there's no logic usually in these systems due to a poor semantic. So each time you have a new situation, basically you end up with a new notation, and that makes you dependent on the notation and of course on the tool, which is not something you want. So what we are wishing is to have standards being used for no code. That would ease communication, because if you're using a standard, if I write something, the others should be able to understand it. It's portable from different tools. Extensible, the notation you're using is extensible, but let's say it's wishfully extensible. Now the problem is that you have an integration issue, because tools usually they support the notation, but then when it comes to integration, it gets tricky, because each integration is specific. So that would mean the tool vendor or the tool editor has to make an integration every time, and that's usually not the case. You have to do it yourself. So that's not helping your users to use standard notation. Also, the notation might not be aligned with the operational concepts in the final system. So you have to be careful to choose the proper notation. Otherwise, it's going to be very, very, very difficult to describe what you're trying to describe. So what we looked at is, well, we looked at languages we are familiar with in our company, in Private. So basically we have tools based on SDL, and the other one on BPMN. So SDL, specification and description language, is a standard from ITU, and it's basically based on state machines with an execution semantics. So if you communicate with something, you receive information and you have to react, it's quite suitable. Okay? But, as we said before, that means you need to be comfortable with state machines. I'm saying that because a lot of people are not familiar with the state machines. So it's not easy to grab the concept and be able to manipulate it. So the example we wanted to make was to use a very basic state machine without any data, because you can have data described in SDL, so no data, very simple. Just send a message, receive a message, and that's all, basically. So what you see here is the initial state in which you can receive this message or this message. If you receive this message, then you can test something. Depending on the result of the test, you can output this or do some other things. and you also have the concept of timers, which in that case, in that example, we can even do more. We can just keep the state and input, and that is enough to describe what we want to do. So what we wanted to do is to use the Raspberry Pi version, that case version 3. You know, Raspberry Pi is ARM-based and has Linux running on it. A version of Debian called Raspbian. So you have the Raspbian operating system. And they have, among the different interfaces, you have HDMI, Ethernet, and so on. But you have this GPIO, the general input-output, general purpose input-output. And that means that you can activate one of the outputs, or you can receive information from one of the inputs quite easily. Within the operating system, you have a Python library, for example, where you can activate the pins very easily. So we made the connection, and we thought, okay, what about saying, I give a specific input name. So for example, I say, my message is called GPIO in 25. That means I'm looking at the inputs on pin 25, which is somewhere here. Okay, and the other way around, if I output a message, GPIO out, give the number, I will output the pin on number 12. Okay? So if you design this in SDL, it will first lower the 18 pin and wait for an input from pin 25. That's all it does. Okay? And when you press pin 25, you can toggle, raise or lower the value of pin 18. So what we did with the board, we put an LED, a button to activate the input pin, and then the LED lights on or lights off. So it's very simple, very direct connection to the GPIO, but it requires the understanding of state machine, which might not be that efficient. Okay. So for us, it was very easy to integrate because we have a tool which runs on Linux. It runs on Raspberry Pi. We just integrated the library that Raspbian is proposing and made the link with the simulator. So you have the animation of the state machine. You have execution traces of what you're doing on the Raspberry. So I think it's very good for, especially for teaching. You know, what is a state machine? What is GPIO? What is Raspberry Pi? I think for education, it's very interesting. It's being used for that. So that's the example I was saying when we had the LED lighting up when you press it. Another example is BPMN. So I don't know if you're familiar with BPMN. Business Process Model Annotation, standard from the OMG. And the idea is to describe, let's say, how an organization works. So it's usually people working together, who's doing what, in which tasks they're doing, how they synchronize with their co-workers, and so on. You could describe actually a technical system with that, and some people do describe technical systems, but it's very high-level view because there's no data or things like that. Huh? It's very high-level, but it has an execution semantic in particular on how when you have parallel execution, it works. You know, do you have exclusive execution or do you have real parallel execution? How do they merge in the end? You know, do they wait for each other or not? And this kind of things, which is quite usual in an organization. So it looks like this. you have, so the example is very simple, right? You have a team member, and you start with that action 1, then action 2, and then you have, so it can be either parallel execution or exclusive execution of action 3 and action 4, and then merge back and do action 5. So you see, it's very, it's quite easy to read. The only thing you have to understand is what we call the gateways here, is how you do parallel things or exclusive things, but it's what's the only thing you have to understand. So if you want to describe something, some process where things are one after the other, and then you have to synchronize with something else, it's quite interesting. So we did this example with a 3D printer. So it's really like a whole demonstration we made with the Chamber of Commerce in Paris, where you have 6 3D printers. You have a robotic arm. So when printing is done on one of the printers, the arm takes the thing, takes it out, shows it to a camera. The camera checks is it conformed, is it okay, no default. And after the inspection, it will put it in the correct box. Okay, good box for so that's the description of what happens in the robotic arm on the top and the camera on the bottom. You see, so the arm is resting. These arrows, dash arrows, are one of the printers saying, "I'm done with printing." So the arm goes up, takes the piece, then presents the piece to the camera. It says, "Okay, please inspect. Is it conform or not? If it's conform, the arm goes to the same box. If it's not conform, it goes to the defect box." Okay. And you also have a description of the different operations for the printers, but the printers are fairly simple because basically the only thing they do is printing, okay, unless there's a problem. For example, if you run out of filament, you raise an alarm, you hang to maintenance, change the filament, and then you raise. So that's basically what it does. And when the printing is over, it only sends one message saying, "Okay, I'm done. Please take the piece out of the tray so that I can print more things." So that's what it looks like. That's the real system. This is one printer. This is another one. So you have 6 printers. The photo. This is the fabric arm. I don't think you can see the camera here. Sorry. What we did is that we made a connection with the MQTT protocol, this very lightweight protocol, to retrieve the information from the system. So the printer box where the 6 printers are was the MQTT server and was sort of conveying all the messages around. And we could receive or send messages to the different operations. So the demonstration we had, where we were actually mainly receiving information in that case, we were following up the execution of the different steps, so you could see where you are, even though you're not in front of the machine, because you can watch that remotely. So we can see, okay, the arm is taking the piece and doing that. Using this very lightweight protocol. So there was an example of describing what's going on in the system, and of course the idea is you could describe yourself and say, "Oh, okay, I'm not doing that. I'm taking the piece. I'm not presenting the piece to the camera. I'm just putting it in the box directly. You can skip, and then it would be easy to change. Where if you have the real system in front of you, it would be quite tricky to understand." How each machine works, how they interact, and so on and so on. So that's another example of a low-code experiment. So as a conclusion, as we said in the beginning, today's notation are low-code tools especially the commercial ones, like Microsoft, for example, that are using proprietary notations, where we believe that some of the existing notations, standard notation, are very good candidates. But as I said, maybe not the whole notation. Huh? But for example, BPMN, if you take the whole notation, might be too complicated for someone who is not familiar with programming. SDL as well. It's too complicated. There might be other notations. So we did this experiment with SDL, connection with the GPIO on the Raspberry Pi. This Industry 4.0 experiment with BPMN and some 3D printers, with cameras and so on. And it's very promising because both of them are working very well. So we are hoping to do more, but also to have other, tools doing it, because to make it work, as I said, you need to make the connection between the notation and the real machines, or the real systems. And that's the real work I have to do, because that's the real added value of low code. Okay, so that's basically my presentation. Thank you.